In the previous lecture, in this series on thermodynamics, we met work. Work, after all, is not a thermodynamic concept. It's a concept which is borrowed primarily from mechanics. But as we said before in the last lecture, any means of transferring energy to a system which is enclosed by adiabatic walls would qualify as work. Let me stress once again that this does not mean that work is not done on systems which are not enclosed by adiabatic walls. If the walls happen to be non-adiabatic, that is diathermal, there would be other means of transferring energy as well, over and above work. But if it is an adiabatic system, then the only means of transferring energy into the system would be via work. Now, we are going to stick to one convention in this series of lectures. We are going to consider as W the work done by the system and not on the system. Now, this work depends in general on the path taken, that is, exactly how you go from one initial state to a final state, and not just on the initial and final states of the process. Specifically, for a simple hydrostatic system, the work done is given by P times dV for an infinitesimal process. And of course, if you have a process which is finite, which changes the volume by a finite amount, you have to integrate P dV to get the result. Now, as you can see from the notation, we have written d cross W for this and not dW. And that's basically because the quantity on the right, P dV, is not an exact differential. It's an inexact differential. And what that means is that there is no real function W, a function of the thermodynamic coordinates, whose differential is given by P dV. No such function exists. In the last lecture, we also saw a condition which will tell us whether a given differential is exact or not. And by using that, it is pretty obvious that P dV cannot be the differential of any function of thermodynamic coordinates. Now, of course, what we said at the very beginning about the work done being path dependent is essentially the same thing as the infinitesimal work done being an inexact differential. If it had been an exact differential, then the integral of this quantity, the net work done, could always be written down as the value of W at the end of the path minus the value of W at the beginning of the path. A result which follows from the fundamental theorem of integral calculus and which also guarantees that the work done would end up depending only on the initial and the final points and not on the precise path taken. We will now turn to the special case of work done by an adiabatic system. Let me stress once again, if a system is enclosed by adiabatic walls, then all the means of transfer of energy onto that system from the outside is basically via work. And it was established in the mid-19th century by James Prescott Joule and others that if a system is enclosed by adiabatic walls, then the work done in any process carried out on such a system will depend only on the initial and final states and is independent of the particular path taken. So while the work done does depend on the path in general, it was experimentally established that under adiabatic conditions, work done is always path independent. Now, this is exactly what we call the first law of thermodynamics. Now, that may seem like a bit of a shock to many of you who have studied thermodynamics before, basically because the common form in which the first law is stated involves a relationship between internal energy, heat, and work. Here we can see no such thing. But let me assure you that this is exactly the logical statement of the first law of thermodynamics. After all, we cannot state the first law in terms of internal energy and heat for the simple reason that unlike work, which is a thermodynamic concept, the very notion of internal energy and heat owe their existence to the first law, to this particular law that work done under adiabatic conditions is path independent. We are going to see that in these lectures. But before we go to that, let me deal with something which is often raised as an objection to this statement. Now, many students would already know that the equation for an adiabatic process is PV to the power gamma equal to constant. Of course, some of you, the more acutely aware of you, would realize that what we are really saying is that PV to the power gamma equal to constant is actually an adiabat for an ideal gas. Granted that the adiabats for other systems may be different, but if we stick to an ideal gas, then what we see from this equation is that there is at most one adiabatic path from an initial state PIVI to a final state PFVF. If PIVI to the power gamma is equal to PFVF to the power gamma, there is a unique curve which can plot obeying PV to the gamma equal to constant from PIVI to PFVF. If PIVI to the power gamma is not equal to PFVF to the power gamma, this curve of PV to the gamma equal to constant will not go through both the points. So, there is one adiabatic path if this condition is obeyed and none if these two resultant quantities, PIVI to the gamma and PFVF to the gamma, are different. Now, what is very important is that if there is at most one path of an adiabatic kind between two states, then saying that the work done is path independent makes absolutely no sense. Independence of the path only makes sense if you have more than one path joining the initial and the final states. Now, this objection is actually quite wrong, and the reason for that is PV to the power gamma equal to constant is an equation for a very special kind of adiabatic path. Even in an ideal gas, PV to the power gamma equal to constant is obeyed only in a very special kind of adiabatic path, and it definitely isn't the only one. Now, in order to establish this point, I will next turn to an example where we will have a gas enclosed in a volume as my system, and that gas we are going to assume is an ideal gas, and talk about an experiment which is sort of very similar to the kind of experiment that Joule himself had done. So let's say we are going to follow the exploits of a modern day Joule who is carrying out a series of experiments on such a system. So the picture here shows a schematic diagram of our system. The gas is enclosed in a cylinder, as you can see, and the cylinder has a movable wall. This wall can be moved out so that hydrostatic work can be done on this particular system or by this particular system. But in addition to that, we have two other means of doing work. There is a propeller which has been introduced inside through a tiny airtight hole on the wall of the cylinder, and this propeller can be rotated by driving a current into the motor here from the outside. Now this is the means of supplying energy to the gas from outside, despite the gas being enclosed by adiabatic walls. So this also counts as work. In addition to that, there is something else which may seem even less like work than the propeller example. After all, in the propeller there is something which is moving around if it's being turned. So there is a mechanical aspect to this work. But the next one, this one, is an even less work-like or less mechanical example of work done. Here you have a resistance put inside the container, and there is a current which is driven through the resistance if you, of course, close the switch here. Now this is also a means of transferring energy into the system, a means by which the surroundings can actually affect the system inside. And so whatever energy is supplied here by this resistor to the gas, that also counts as work done on the gas, and of course negative work done by the system. The system here, remember, is a gas enclosed in this cylindrical region. Now, experimenters, let's say our modern day Joule, observe the following results. If the propeller is not turned and the resistance has no current through it, but if you draw this piston out very, very slowly, the pressure of course falls as the volume expands. But experimentally, by attaching pressure gauges and maybe having graduations drawn on the cylinder so that the volume can be measured, our experimentalist friend finds the following. The law which this gas obeys as it expands is given by P cube times V to the 5 equals constant. So this is a purely experimental finding at this stage. Now, another way of doing adiabatic work on this system would be by turning the propeller while keeping the resistor switched off as well as the movable wall here fixed. So the wall has been clamped. Now the propeller is being turned. Now again, our experimentalist friend finds that as you do this, the pressure of the gas inside increases with time. And the rate at which this increase occurs, dPdt, is given by 2/3 times omega tau by V, where omega is the angular velocity with which the propeller is turning, tau is a torque acting on that, and V is the volume of the gas, as before. And finally, when our third means of doing work is switched on, that is, wall is clamped, the propeller is stationary, but a current I flows through the resistor R because the circuit has been closed, then our experimentalist friend finds that pressure increases with time once again, and the formula for that he finds is 2/3 I square R by V for dPdt. Now, each of these steps, of course, there are different situations where work is done adiabatically on the system. So here you have several means of doing work on the system despite it being enclosed by adiabatic walls. Let us now consider a bunch of paths. The first path is one which takes you from PI-VI to PF-VF via an adiabatic slow expansion, the part which obeys P cube V to the 5 equal to constant. This of course takes you to some final pressure when the volume reaches Vf, and then you switch on the propeller, and as the propeller churns, you end up with an increase in pressure, and finally the pressure reaches Pf. Remember that here the movable wall is clamped and therefore the volume does not increase any further. So whatever volume has been reached here has to be Vf in order for you to be able to get up to this. The process shown in B, this graph, is very similar. Starting from PI-VI, you expand the gas until it reaches the volume Vf as before, and then instead of turning the propeller, you actually switch the current on in the resistance, and in this dashed line marked R, the pressure is going to rise according to the rate that we have already talked about before. Note that in this case both the vertical lines have been drawn as dashed lines because here the initial state is in equilibrium. If I draw the thing sufficiently slowly, at the end when the volume reaches Vf, the system is in equilibrium, and the final state once it reaches PFVF, everything can settle down. This of course occurs not as the propeller is turning, but once the propeller has been switched off, after a while the system reaches this steady state of PFVF. And frankly, you don't really know exactly what the state is in the intermediate stages because the gas was not in equilibrium in the intermediate stages. So while the expansion has been drawn slowly enough so that you can think of each intermediate stage, if not as an equilibrium state, but a state which is very close to equilibrium, so you can draw a continuous line for that. For the propeller churning or for current flowing through a resistor, you can't really think of the system as a quasi-static one. So you should not really be drawing a solid line which would indicate that all the equilibrium states on the path are really being visited there. Okay, the third of our processes is sort of a combination. You go from PIVI to PFVF via an adiabatic expansion first, the slow adiabatic expansion that we have talked about. Then you increase the pressure by turning current for some time through the resistance. Then you expand this adiabatically slowly once again until you reach the final volume. And now you churn on the propeller, keeping the valve clamped, to reach PFVF. Well, figure D here shows something which is a bit more complicated, but essentially the same idea. You expand slowly until you reach a particular volume, then you turn on the resistance, pressure rises to this point, then you again slowly expand this out, then you turn on the resistor once again, then you finally expand this out until it reaches volume VF, then clamp the valve and just turn the propeller on so that ultimately the pressure PF is reached. The question is, what is the work done by the gas? Remember, we are always going to use by the system as a positive number. So if it comes out negative, it means work is being done on the system. So what is it for each of the four cases? Now, rather than work out the four cases separately, what we should first do is figure out how much is the work done for each of the three situations that we have talked about. The situations which are marked E for expansion, P for propeller, and R for resistance in these graphs in front of you. So first, let us work out the work done when a gas is expanded slowly. Remember, our experimentalist friend has already found out that when this gas expands slowly, it obeys the equation P cube V to the 5 is constant. We will just rewrite that slightly in this form. P times V to the power 5 by 3 is a constant. Let's call that K. Now, if under such a process, the gas expands from an initial state given by P1 V1 to a final state given by P2 V2, then we can easily calculate the work done here because the work done in this case is purely mechanical. The hydrostatic work done given by the integral of PdV. Note that this is the work done by the gas in the process, and that is what we are actually calculating throughout. So it will be an integral of PdV from P1 V1 to P2 V2. Now, in order to carry out the integral, we need to reduce this to a single variable, and that's easy to do. P here is simply K V to the minus 5 by 3, which we have plugged in here. And this is pretty easy to integrate. K being a constant comes out of the integral. V to the minus 5 by 3 essentially becomes V to the minus 2 by 3, and then you have to divide, of course, by minus 2 by 3. Therefore, you get minus 3 by 2. This is the indefinite integral for K V to the minus 5 by 3. And you have to put in the values of the volume, which is the only variable here, at the beginning and at the end. And of course, subtract the first result, the one at the beginning, from the second result. And therefore, you simply get minus 3 by 2, K into V2 to the power minus 2 by 3 minus K into V1 to the power minus 2 by 3. Now, K is either equal to P1 V1 to the 5 by 3 or equal to P2 V2 to the power 5 by 3. Of course, both of these numbers are exactly the same. And what we are going to do now is play a little trick. In this part of the expression, I'm going to replace k by p2 v2 to the power 5 by 3. That's what I've done here. And in this part, the second term, I'm going to replace k by p1 v1 to the 5 by 3. And it's easy to see why we are doing that. Here the two volume terms combine to give you v2 to the power 1. And here they combine to give you v1 to the power 1. So your result becomes very, very simple. It's plus 3 by 2. Because I have changed the sign here from this minus to plus, it means that I have had to swap these two terms. And you've got P1 V1 minus P2 V2 as your final result. So under this slow expansion, the work done is given by 3 halves of P1 V1 minus P2 V2. That is what our experimental findings tell us. Okay, what about when you clamp the wall and switch on the propeller? Now here the work done is again mechanical, but not hydrostatic. It's not PDV. In fact, here you're going from P1V to P2V. The volume V stays fixed here, and PDV work for that, of course, is 0. However, when something turns around under a torque, we know from mechanics that the work it does on the surroundings is given by tau d theta's integral, where d theta is the infinitesimal angular displacement, and you have to integrate this from the initial angular position to the final angular position, from theta 1 to theta 2, to get the net work done on the gas. But because here we are talking about work done by the gas, I have to add an extra minus sign in the front. So our expression, the one we are trying to find out for this particular kind of path, the path P, is integral of tau d theta from theta 1 to theta 2, but with a minus sign in front. Now this is pretty easy to work out because tau d theta can be replaced by tau times omega dt, d theta being simply the angular velocity times the time interval. And now comes our experimental result. Our friend had found out that dp dt, the rate at which pressure increases with time under such a situation, is given by 2/3 omega tau by v. Using that, we can replace the omega tau here and get 3 by 2 v dp dt here for this integrand. And now, remember, v is a constant for the process, so it can just be pulled out. So you get minus 3 by 2 v times the integral from t1 to t2 of dp dt times dt. That's of course dp here. So when you integrate that, you just get p, and the limits of course change from the limits of t1 to t2 to the corresponding pressures. Minus 3 by 2 v p, in which you have to substitute p2 and p1 and subtract to get the final answer. And once again, because there's a minus sign here, you switch the order and put the lower limit expression first, and you get plus 3 by 2 P1V minus P2V for this particular kind of process. The third kind, the resistor, should be even easier to work out. After all, here the work done is purely electrical. Again, the system is going from P1V, some initial pressure, a given volume, to P2V, same final volume, an increased final pressure. And here the work done on the system, once again, is given by the amount of energy supplied by the resistor, that's I square R dt in an infinitesimal time dt. But that's work done on the gas. We are calculating work done by the gas. So we have a minus sign all over again. And now our experimentalist friend has told us that under such a situation, the pressure increases at a rate given by 2/3 I square R over V. And using that, we can change the I square R to be 3 by 2 V dp dt. And now this calculation is exactly the same as the previous one. And you get 3 by 2 times P1V minus P2V as the net work done by the gas when this is occurring. Note that in both of these examples, P2 is bigger than P1, and as a result, the net work done by the gas is negative in both cases. That's really not very difficult to understand. In both of these cases, we are actually transferring energy into the gas. So it's really work done on which is positive, and so the work done by the gas works out to be negative expressions for both the cases. In fact, even the previous one, for the slow expansion, it does turn out that here too you actually have P1V1 as less than P2V2. Note that PV to the power 5 by 3 being K, PV, the product, is K V to the minus 2/3. So it decreases whenever the volume goes up. This system, as you must have guessed, is an ideal gas, and it started out at a particular temperature given by P1V1 by Nr. It has dropped its temperature during this expansion. And hence, for the expansion that we have talked about, even this particular work done is negative. However, there is a big difference between this particular term and the other two terms that we have calculated. Note that in the other two cases, the pressure could only go up as you churn the propeller or turn the current on in the resistor. So in both cases, the work done by the system has to be negative. Here, on the other hand, instead of slowly expanding the gas, could have also slowly contracted the gas, in which case, of course, you will get exactly the opposite result and the work done would then become positive. Once again, note that we are talking in each case about work done by the system, not on the system. So now let us come to our first path, purely adiabatic path of going from PIVI to PFVF. Remember, here what we are doing is we are slowly expanding the gas by moving the piston until it reaches some pressure P prime, but more importantly, it reaches exactly the volume VF, the final volume. And then we switch on the propeller and the propeller does its work. Ultimately, the pressure rises from P prime to PF and you have got to this particular final state that we wanted to attain, PFVF. So now, what is the net work done for this process? It's very easy to figure out. We have already figured out the work done for each individual part. The work done during this expansion, as we had figured out, is 3 by 2 times P1V1 minus P2V2. So here P1V1, the initial PV values are PI and VI. That goes here. And the final PV values are P prime and VF. So P prime times VF goes here. So that's the work done for the adiabatic expansion, slow expansion of the gas. But then comes the other adiabatic work done, which happens because you have switched on the propeller. And that, we had figured out a while ago, is 3 by 2 times pressure initially minus pressure finally into the constant volume. So P prime VF minus PF VF. Note that when we add the two together, this P prime thing neatly cancels out, so we don't even have to figure out what that is. You just add them, you get 3 by 2 PIVI minus PFVF. A rather simple, straightforward result for the net adiabatic work done when you follow this particular path. Now, I could have worked out the result for each of the paths, but frankly, that will be a bit boring for you to listen to. But just to illustrate that paths can be much more complicated than this one, what we can always do is take a look at one more. Let's say the part that we showed as part C. First, an expansion which I've marked as E1, which takes PIVI, the initial state, to P prime V prime. Then you turn on the resistor, so you get to P double prime V prime. Remember, the volume stays the same. It's only the pressure which rises. Then another slow expansion, the one marked E2. Then you switch on the propeller. Of course, at the end of E2, you have already reached the final volume that you want to get to, this VF. So, whatever this pressure is, P triple prime has to increase slowly as you churn the gas with the propeller and finally reach the pressure PF. So here, the work done in the expansion is simply 3 by 2 times initial PV minus final PV, Pi Vi minus P prime V prime. When you switch on the resistor, it's 3 by 2 into actually initial PV minus final PV. It's just that here the V is throughout constant. So P prime V prime minus P double prime V prime. For the expansion that follows that, it's 3 by 2 times initial PV, P double prime V prime minus final PV, P triple prime Vf. And finally, when you turn the propeller on, you go all the way up here and you get 3 by 2 times P triple prime Vf minus Pf Vf. And when you add all of these together, these terms simply cancel each other out. So all these intermediate values for the pressure and volume, P prime, V prime, P double prime, etc., all of them just cancel out. And you are left with a work done, which is simply 3 by 2 Pi Vi minus Pf Vf. So I hope I've convinced you that in these two cases, both of which are adiabatic works, the process is entirely adiabatic. When you add up all the contributions together, you actually exactly get the same result every time. Of course, this is one example, or rather a couple of examples, but I might even argue that this is really infinitely many examples rolled in one, because I did not really tell you what volume the initial thing expands to. So if you change the V prime, you will end up with many different possible paths, even within this particular example. Now, I'm pretty sure you should be able to figure out in the other two cases, the cases B and D, which have not worked out here, that the work done ultimately works out to be exactly the same. Now, in case you have not already guessed, and it will be very difficult not to guess this because I've actually mentioned this already, the system that we are talking about is an ideal gas which obeys the equation PV equal to nRGT. Here I have written Rg for the universal gas constant simply to differentiate it from the resistance. N, of course, is the number of moles of the system, and T is the ideal gas temperature scale temperature. This equation is called the mechanical equation of state because it relates the temperature to pressure and volume. We have already seen this before as basically the formula for empirical temperature using an ideal gas thermometer. Now, of course, if this is a real experiment carried out, our experimentalist friend would have to use a real gas for the experiments. Ideal gases don't really exist. But under the right experimental conditions, the system closely approximates an ideal gas. So even real gases do behave like ideal gases, especially if the temperature is high and the density is low. So, within the limits of experimental precision, our friend's results thus show that work done to take a system from a given initial state to another fixed final state is independent of the paths taken. Now, if these were the only experimental results in favor of this law, then frankly we would have a hard time really believing that the law is correct. The reason why we believe in the first law of thermodynamics is that it is a culmination of many such experiments, not just one or two. And the net result of all of these experimentations shows us that under adiabatic conditions, the work done is path independent. Now, this is a statement about the nature of the universe, which the universe could very well have not obeyed. It is very conceivable that under adiabatic conditions, work done would be path dependent. But that it is not is a physically significant statement. In fact, one of the most physically significant statements of all time, the first law of thermodynamics. Now, the concept of internal energy has not entered into the discussion at all. Neither has the concept of heat. As I promised, these are concepts which will actually arise from this version of the first law. But we will have to wait till the next lecture to discuss this.